2.
So, hello everyone. We'll just be starting in a few minutes. There's a lag. Just let me fix this. Trying to fix my camera to see if there is an issue with the video. Okay, so we'll just start in a minute or two. I think it's almost time. And we'll discuss mostly extensive form games today. We won't discuss too much of what we've discussed earlier unless you have any specific questions about what we discussed earlier. So, just see. Yes. So if you have any questions about week 4's content, or like if you have any questions from earlier weeks, the exercises and things like that, you can let me know. If not, we will go ahead to week 4's content. And if there is any specific doubt you have, I'll discuss that and I'll keep that in mind. So I'll just allow a few minutes to people to join and then we'll start. Okay, so It's been a few minutes. I will start the class, and if in case somebody joins later, we will cross that bridge when we come to it. Okay, so let me share my screen. How to make this full screen. Okay, it's fine. I think we can work with this. Okay, so in the previous classes, this is what we have covered so far. And I'm not going to be discussing much of this stuff. Sorry, just one second. There's some problem with this stupid webcam. Yeah, let's use a simple camera. So let's go with what we need to do today. So first of all, this is the first class in which we are going to be discussing extensive form games properly, because in the previous classes, we just kind of barely touched extensive form games, and we didn't really get much into it. So first of all, let's see what extensive form games really are and how are they different from the normal form games. So first of all, it's important to understand that extensive form is a representation of a game. It is not necessarily a separate game. So an extensive form game can, and we generally will, represent it in the normal form also. How we do that, we'll discuss. It's of course there in the lectures, but I will discuss it also. And the reason why we treat extensive form games separately, we understand the methodology separately, is because these games generally involve some sort of a sequence. The players are taking decisions in a sequence. And there is a sort of like what we call a game tree, as you can see on the screen. There is something like a game tree in which, if A takes this action, then B is going to take that action, so on and so forth. So, sorry, just give me one moment. So that's how it's different, and which is why if you take it in the normal form, like how you normally do it or like how you have done it till now using a game table, you may get some incorrect results, or you may get some results which are not exactly valid in this type of a game. So I'm taking a very simple game first, and I'm not taking a very complicated game, just to explain the concepts and to make sure we understand the fundamentals. This is a simple game. It is from the book by Martin Osborne, and it's like just a two-step game. There's no multiple complicated things. So let me just get down to, let's open the notes also. So let's start with the question we have first, question 1, in which we'll first take a look at backward induction and what it is. Okay. So let me draw the tree or the game again. This is the game. This is the first node. You can call it the root node or the initial node also. Here, player one. I'm putting one. It means player one is taking the action here. And so there are two possible courses of action for player one, C or D. These are the two strategies. At C, player two needs to take a decision. So this is a decision node where player two is going to act, and same over here. Here, player two has strategies E and F. And here he's got strategies G and H. The payoffs are 2, 1, 3, 0, 0, 2, and 1, 3. Okay, so this is the game. Now, what we want to do is we want to find out, first of all, how can you write this game tree in the normal form, the form we have been using till now, the game table form. Secondly, what are the, let me write down what we want to do. Game table. First of all, we want to make Nash equilibrium and subgame perfect equilibrium. These are the three things I want to find out. So now the way in which we'll proceed here is very different from what we have been doing till now. And the way we proceed is, first of all, to identify the strategy. That is not different. That is not the part which is different, but the way we write the strategies is different. So player one has only two strategies, which is C or D, right? That much is clear. Now player two has 4 strategies. Is that so? So now he has strategy E or F at this node. Let's call this node N1, N2, N3, just for identification purpose and just so we are all on the same page. So at node N2, player 2 has strategy A and F, and at node N3, he has strategy G and H. But we will not write it as just E, F, G, H, right? We are going to write this in a different format in which we can actually identify all the strategies available to player 2. Okay, so we'll come to that. Now, first, let's see what happens when we start with backward induction. And backward induction, as the name suggests, means you're starting at the bottom, at the lowest part of the tree. Lowest meaning at the terminal node. So these are your terminal nodes. All the nodes where you have payoffs written are terminal nodes. Let me write this in some other color. This is a terminal node. Okay. And we'll start the game, first of all, at the terminal nodes. We'll not start at the top. Now, let's see. Now, at node 3, let's see, N3, player 2 is the one who's deciding, right? Now, between strategy G and H, which one gives him a higher payoff? Only 2. This one gives a higher payoff to player 2, right? So this is what he's going to do. The game is going to proceed in this direction if this part of the game gets played. Now, which is the other terminal nodes? The nodes after N2 are the 2 terminal nodes. If the game proceeds in this direction and player 2 has to decide at N2 which strategy he should be playing, he's going to play the one which gives him a higher payoff, right? Player 2. So he gets a higher payoff for E. So he's going to play E in this direction. Right? He's going to play strategy E because that's what gives him a higher payoff. Now let's see from the point of view of player 1. Now, if player 1 has to choose between strategy C and D, he has to compare his payoff, right? Now, he knows that at node N2, player 2 is the one deciding. Player 1 is not the one who's deciding. And player 2 is deciding to pick their highest payoff, and which is strategy E, which gives a payoff of 2, 1. So the payoff that one can get from choosing C is 2, right? Now, if player 1 decides to choose strategy D, then he knows that player 2 is going to choose strategy H, right? He's going to choose strategy H because that is what gives player 2 the highest payoff, and the payoff player 1 is going to get from choosing strategy D is 1. Now between 1 and 2, 2 gives higher payoff. 2 is higher payoff for player 1. So this is going to be your equilibrium, your Nash equilibrium, and also your subgame perfect equilibrium. Now let us see how we can write this as a game table. We've only written this as a game tree right now. So the first part is pretty simple. Player 1 has only 2 strategies, C and D. Okay, C and D. Now we will write the strategies of player 2 considering both the subgames, right? This is, I'm just going to draw one line and I'll delete it later. This is one subgame, this is another subgame, and the whole game is one more subgame. So this has 3 subgames, this whole game. Let's write that down also. Okay, let me delete this. I don't want to make it messy. So now when you write the strategies of B, you have to write the strategy of B for every subgame that, considering every subgame that B, sorry, not B, 2, considering every subgame that player 2 might need to play. So you have strategies EG, EH, FG, FH. Okay, so EG, EH, FG, FH. Okay, and why we are writing it like this, you'll just understand in a moment why it's important to write it like this and not in some other normal way which you have been writing till now. So now let's see, if player 2 is playing EG and player 1 is playing C, then what is happening? He is playing E and G, and 1 is playing C. So what is the payoff here? 2, 1. If he is again playing EG and player 1 is playing D, then this part of the game is getting played, right? Then the payoff becomes 0, 2, right? This is why we are writing both the the strategies in both the subgames, because which subgame gets played is decided by player 1's strategy. Okay. Similarly, now let's go to the next strategy, EH. Oops. Okay, let's read that. Okay, let's go to EH. Okay, I'm just marking it temporarily for explanation purpose, just so we know which part of the subgame we are in. So 2 is playing EH. 1 plays C means E part of the game is getting played. So the payoff is again 2, 1. And EH means the other subgame gets played. So the payoff for is 1, 3 when 1 is playing strategy D. Okay, now let's erase this from now. 1 is playing C and 2 is playing FG. FG. Okay. 1 is playing C means R is getting activated, so to say 3, 0, and 1 is playing D. So G is the strategy we're talking about for player 2. So this is 0, 2. Is this clear how we are getting the game table? I just want to stop here to make sure we understand why we are writing the strategies in this way and why the game table is in the way it is written. How we are writing the extensive form into the normal form. Okay, so let's do the last part also. FH. FH. So FH means if 1 is choosing C, then this is 3, 0. And 1 is choosing D, then 1, 3. This is your This is your game table. Now in this, if you want, you can, now this is basically, this answers the first part of the question, which is writing the game table. This is your game table, also called the normal form of the game. Now we need to find the Nash equilibria. It's not that difficult. So if one is, if one is playing strategy C, what is the best response of 2? One is playing strategy C. So for player 2, both of these are going to give you the best responses. His payoff is better here. If one is playing strategy D, the best response of player 2 is this. And let's see it from the other perspective. If player 2 is playing EG, one would rather play C. If he's playing EH, one would again play C. If he's playing FG, one would play C. FH, also C. Now you can see that you have two Nash equilibria, right? Nash equilibria are your C, EG and C, C, EH. Okay, these are your two Nash equilibria, but we need to find which one is subgame perfect. And subgame perfect means that if that subgame is actually played, are those the strategies which the two players are actually going to choose? So because see, in the normal form, we have written all possible strategies, right? All possible strategies in all the subgames. In the subgame perfect equilibrium, what is actually going to be played in that subgame, if that game is played by the two players, only that can be a subgame perfect equilibrium. Now let's see, if one is playing C, 2 would play E, right? And if one is playing D, then this subgame, 2 is going to play H. 2 never plays G, right? E is okay because 2 is going to play strategy E in the first subgame, but in the second subgame, 2 is not going to play strategy G. If this subgame is actually played, if this subgame pans out, then 2 is not going to choose the strategy G. He's going to choose the strategy H. He's clear about that he's going to choose what gives him a higher payoff, right? Therefore, even though as per the game table, you may get EG and EH both as CEJ, CEH both as Nash equilibrium, the equilibrium of CEG never gets realized because G never gets played. Therefore, your subgame perfect Nash equilibrium can only be C, EH. The one is not subgame perfect. Okay, so I hope that much is clear. Okay, great. So let's move on. This is the first question. Let me go back to where I'm here. Right. This is another game which I think Professor Vimal discussed this in the class, but partly he didn't discuss like the whole game. He left it to us to solve it. So I thought I'm going to discuss this also because this is it's a very good game for illustrating the basic concepts of backward induction and subgame perfect equilibrium. So let's draw this game. Okay, so this question is also from Martin Osborne's book, and I've actually just taken it as is. Let me just draw this first. One is acting here, and these three nodes, player 2 is taking the decision. Here he has the choice of F, G. Here H comma I. And here J comma K. So these are the payoffs. Okay, so this is the representation of the game. Okay, so now let's see how many strategies does player one have. C, D, and E, right? That one is pretty clear. And player two has these three subgames in which he's taking the decision. So let's mark the subgames also here. So this is one subgame, this is the second, this is the third, and the whole game is another subgame. So there are 4 games. It's important to understand what is a subgame and what is not a subgame in a particular question, because you have to check for the subgame perfect equilibrium. If it was not a requirement to check the subgame perfect equilibrium, then it wouldn't matter. But since it is a requirement, you're asked the subgame perfect equilibrium, you need to know and identify how many subgames are actually there. So let me see if this yellow is actually visible. Okay, so yellow is not visible on this background. Okay, I'm leaving it for now. I will change this color later on because yellow is not visible. So when I export the file, it won't be visible. Okay, all right. So let's first look at the game. Looking backward. Okay. So if player two, let's look at the last subgame, has to choose, if player two is choosing between J and K, his choice is pretty straightforward. He gets a higher payoff here. So he's going to always choose K. Okay. Now, if he has to choose between H and I, he can go both ways because he has same payoff in both the ways, in both the strategies. And similarly, if he has to choose between F and G, they're both his best responses. He can go either way. So what we do in such a game, just to simplify our lives, is that, in this last subgame, the choice is clear, right? So we remove this whole subgame and we just condense it to, we can sort of ignore this part, okay? Because only K is chosen and J is never going to get played. But this and J is not really a best response in any situation. Only K is going to get played. So we remove that. We don't have to remove it, but we can just ignore that part. And we just identify this payoff for this leg of the game. So when we're writing the game in the normal form, we can just write it as FHK, FIK. We don't need to write the J part. But if you're asked all the Nash equilibria, if this is, I'm saying this if you're only using backward induction to solve for subgame perfect equilibria. But if you're asked all possible Nash equilibria, this is not advisable because sometimes the answer may be a bit counterintuitive. So for now, I'm going to write everything just to make sure we are not missing. Actually, in this particular example, you're not going to be missing any Nash equilibrium, even if you remove J. But just to illustrate how to go about it, I will write all of them. Okay, so one has strategies C, D, and E. Okay, so we will write the strategy of 2 for every subgame, meaning the strategies are going to be F, H, K, F, I, K, then G, H, K, and G, I, K. Okay. Now I will add the last part also it just adds 3 more rows to it or 4 more rows to it. F H J G H J F I K J G I K J, sorry. So it'll add 4 more rows if you add the J strategy profile also, which is why I'm not doing it in this particular example, because I mean, I have already solved it, so I know that there is no Nash equilibrium for it. But I would advise that if you need to do that, if you need to solve for Nash equilibria, it's better to do that for all the profiles, strategy profiles. Okay, so let's see now. If 1 is playing C and 2 is playing FHK, the payoff is 3, 0. 1 is playing D and he's playing FHK, the payoff is 1, 1. And if 1 is playing E and he's playing FHK, it is 1, 3. All right. Now 1 is playing FIK, sorry, 2 is playing FIK, and 1 is playing C, it is still 3, 0. Here it is 2, 1. Here it is 1, 3. Right? Then we have G, H, K. C, if 1 is playing C, this is 1, 0. G, H, K. K. And then you have G, I, K. Okay. G, I, K. So this is your normal form table. Okay. This is pretty simple. If you want, you can, like I said, if you want, you can extend it. You can use, you can use the extra rows. If you want, if you're confused about it, I will add it in the end. But okay, sure. So if you want, if you're still confused about that strategy J, we can add 4 more rows in the end and see if it makes a difference to the game. And some games it may make a difference. And just for the purpose of neatness, I'm removing it for now. Okay, let's see now. If player 1 is playing C, then for player 2, they're all best responses. 1 is playing D, then again, they're all best responses. Wait a minute, then do something wrong. No, just right. Okay, 1 is playing E, then also all of these are best responses. Now let's look at it the other way around. If 2 is playing FHK, 1 would play C. 2 is playing FIK, again C. If it's GHK, all these are fine. GIK, this is 2, 1. Right. Okay, so now you can see that, the boxes or the cells in which you have both the red, the pink and the blue circle, those are all your Nash equilibria. So if you want, you can write it here. Nash equilibria are C, FHK, C, FIK, C, GHK, and then D, GHK, then D, G, I, K, and E, G, H, K. Okay, all of these are your Nash equilibria. Now, we don't want to just leave it here because we want to find the subgame perfect equilibria. So let's see, C, F, H, K. Can it be played? Can it be played? Yes. Right. This is so if one has to choose between all of these, then CFHK is going to be played. Just 1 minute. And then actually I forgot where I took the question from. Oh, this is Osborne. Actually, this is just so you know, this is a solved question in Osborne. And what I've solved here, it's pretty much the same what we have done, but I've just given it a little bit more detail. We've not made the table and all that. So you can see that, you can compare and see if you are getting the same answer or not. I'm just checking if I'm, if I'm missing something. I don't, but I think it's correct. So, okay. Okay, so let's see. So let me look at the game. So C, F, H, K. So now you see, when we were talking about the two subgames, the second two subgames, we were clear that, between F and G and H and I, both are played by the player two. So strategies which have F, H, F, I, G, H, G, I, and which have, K, all of them are going to be rationalizable. They're all subgame perfect, right? Which is why when we remove J in the beginning, we don't actually run into trouble, because if you had some equilibrium in which you had the strategy J, then that would not be subgame perfect, because strategy J is the only strategy which we know is never going to be played. Okay, so that's why we kind of isolated it. If you want, let's do the grunt work. We can, of course, do F. I just want to illustrate the point. I was just checking it is not illustrated in the book. So let me do it here. F, G, H, J, F, H, F, I, J, and G, I, J. Okay, if you want, you can extend it like this. And let's see now. One plays C, two plays F, H, J. This is 3, 0. One plays D and he plays FHJ 1, 1. One plays E and this is 2, 2. GHJ GHJ F I IJ, right? 2, 1. GIJ. Okay, now let's see if you are getting any extra additional. So these are all the best responses from 2. Okay, these are not the best responses, so we are saved there. Here, this is the best response, okay, of 1. I'm just doing it a bit fast, so I'm not explaining much, just so you have an idea of what we are doing here. I've just marked more best responses of both the players, 1 and 2, okay. Now see, in this part of the table, let me just highlight this part of the table. In this part of the table, any of these, these are Nash equilibria. Any of these Nash equilibria which you get are not subgame perfect, because the strategy J never gets played, right? So this is what I was just checking if this is explained in the book. It's not there. That's why I wanted to add it. So this part, if you want, I will add this here, just because we're writing the Nash equilibria, then we will write this also. C, comma, F, H, J is also a Nash equilibrium. C, comma, oops. C, comma, F, I, J. And there's one more, I think, D, G, I, J. Okay, so these last 3 are not subgame perfect. This part I hope is clear now. So I made the whole table just to explain how you calculate all the Nash equilibria and how you calculate the subgame perfect equilibria. So generally, this situation may or may not arrive. But if you're asked only subgame perfect equilibria, then if you remove this profile J and you just instead replace it with strategy K and pay off 1, 3, then you're good. You don't have to do anything else. But if you are asked all the Nash equilibria of the game, then you will add this whole table, all the possible combinations of the strategies, and you'll do the usual best response analysis. And this is all the Nash equilibria you will get. Okay. So I hope this explains like the concept of subgame perfect equilibrium and how it is different from Nash equilibrium. Okay, so let's go back to the questions. And any questions so far? Okay, I'm assuming no questions. Okay, so next we come to a slightly different type of game in which the player 2 has played one of the strategies A or B, but player 1 does not know which strategy has been played, and player 2 in the second part of the game has only two strategies, X and Y, at both the nodes of the game. Okay, so let's draw this game. It's trying to fit the thing. Okay, let's draw it the way it is given. So this question is from Joel Watson. Okay, this question is, I think, an unsolved example in Joel Watson. And I think there are other questions also sort of like this question, but like not exactly this question, but similar questions are also given in Joel Watson if you want to practice. And in these questions, extensive form games, the more you practice, the more, the concepts will be cleared out in your head, because in game theory, there's not really that much of theory. It's literally, we call it game theory, but in my opinion, it's more game and less theory. There's very little theory in game theory. It's all game. So do more of games and the theory will automatically be clear to you. So wanted to take one game of this type so that you are sort of clear on how to deal with these type of games. So here player 1 has two options, X, Y. And important to remember, move this out of here. He doesn't know which node he is on. Okay. So I'm making this with like a dotted line, but in some books, you might see that they have circled it like this. So that's like, it's a similar notation. It's not that hard and fast. Generally, you will find the dotted line, but some places you may find that they have circled it like that, sort of like the same thing. Okay, so let me write the payoffs 3, 0, 5, 1. Okay, let me move this a little. Just give me a moment. I'm just scaling it because when I export this file, it's going to otherwise look weird. So Okay, so I think this is clear enough now, the table. It's not that messy. So let's, look at what, what are the strategy profiles. So I think I've been talking for some time. So why don't you tell me, Mukesh, I think your name is, right? Yeah. Why don't you tell me what are the strategies of player one and player two? What strategies do they have in this game? You're the only active participant in my classes. So unfortunately, I can only ask you the question. For some reason, people are not joining the classes, but either way. One is WX and WY. Is that all? Is that all the strategies one has? ZX and ZY. Yes, good. And two, what strategies does two have? Uh, so we'll write the strategies of two in the same way that we wrote earlier, right? We wrote strategies of player two, considering every game that the player might be playing. So I'll just give you a moment to think. Okay, just try to write the strategies the way we wrote till now. So you're saying DB, DA, CB, CA. Yes, that's correct. So you can write, so in this particular type of a problem, you can write A, D, B, D, B, C, A, C also, like either is okay. So let's write down the strategies in the normal form game first. And it's important to note that, we cannot solve this question with only just simple backward induction, because there is imperfect information. We don't know which node player one is on. Is he on the node after strategy A, or is he on the node after strategy B? So whenever you are solving an extensive form game in which you see this dotted line, and if it is a discrete game, not a continuous game, mostly for you, or at least in this course, you're unlikely to encounter games which are in continuous time, in which are continuous numbers and uncertainty, but it can happen in other places. So in those places, we'll come to it, how you do it, but let's just first write it for this game which we are given. So you see, I'm writing it from top to bottom. So I'm writing A, C, A, D, but what you wrote is also correct. You can interchange the letters. That is fine. Okay, so my game table is a little less. This is better. So let's look at the game. Okay, let's see what happens in each condition, and that is how you solve the game. So 1, let's mark 1 and 2. 1 is playing W and then X, and 2 is playing A and then C. We are following which path? W and then X, right? And 2 is playing A and C. So this is where we end up. So the payoff is 3, 0. And W and if we're following Y instead of X, we end up here, right? So this is the payoff 8, 5. Right? This is important even more in these type of games, because in these type of games, the player 1 in this particular case does not know where he is. Only player 2 knows where he is. Okay. So if player 1 is playing Z and then X, this is Z and then X, and player 2 is still playing AC, then this leg of the game is getting played. So you have 6, 4, and this is also 6, 4, right? Yes. Erase all these extra lines. Okay, A, D. Okay, A and then D. So again, we are still in the top part of the game. For WX, it is still 3, 0. WY, it is still 8, 5. When we talk about A, D for player 2, and for player 1, we are saying ZX, it is 6, 4. Oops, sorry. Saying AD for player 2, right? AD. So this is not 6, 4. This is 3, 2 and 2. Right? Yes. Okay. Then we come to B, C. So I know I'm sort of like, talking while writing the table just to explain what I'm doing. And it's important to write this part a bit slowly. So even if you're really short on time, just pay very close attention to which strategy, which subgame is being played corresponding to the strategy you have written in the game table. So W, X, B, C. So W, X, X, B, and C. So if BC is getting played, then the second node, this node, is getting used. So this is 4, 6. And WY for BC is 2, 1. ZX, BC, C. So this here, ZY, BC is still 6, 4. Okay, WX, B, D, X is, sorry, B, D, right? So 4, 6. WY, 2, 1. Z, X, and B, D. So this is 3, 2. Z, Y, and B, D, 2. It slightly not complex per se, but just requires a little bit of focus. Otherwise, it's very easy to make a mistake in this table. So if you get this table right, like most of your work is already done. Like this is not too much to worry about. Let's look at the other game. This game, we know that, this part of the game, we don't know what is going to happen because player 1 doesn't know which node he's on. But let's look at the other subgame. In this game, player 2 who's deciding, and we know that for player player 2, this is a better payoff. So we know that this part of the game is going to get played. Strategy B will not be played by the player 2. So this part, this rationalizing this aspect of the game is still important, because when you're trying to find subgame perfect equilibrium, you need to make sure that those equilibria are actually getting played when that game is played. So let's look at this again. If one is playing strategy WX, what is the best response of two? This and this. For WY, this and this. ZX, this, ZY, this. And let's look at it from the other way around. Okay, so these are your, you can see you have Nash equilibria, I think. Let me check if I'm correct. We have 4 Nash equilibria. And we will now check which ones are subgame perfect. Okay, so we know that strategy D does not get played. Okay, so the ones you have strategy D are not subgame. I'm only writing subgame perfect equilibria, because the others you can see from the diagram itself. Okay, so you have WY, comma, AC and WX, not BD, sorry, not WX. This is ZX. X, comma, BC. These are the only 2 subgame perfect equilibria. The other 2 are Nash equilibria, but they're not actually going to be played in the real game if the game is actually played in that part of the subgame. Okay, so any questions? Hope this is clear. Okay, so if it is clear, then I'm going to take a short break here. We'll take a 5-10 minute break. And let me open the. So I will, in the meantime, you can look at the Centipede game or Centipede-like game. Centipede game can actually be, well, it is a Centipede game, but except that in Centipede game, you generally have many more decision nodes. And this is one with fewer. Okay, what did you ask? Except C, D, we have solved without making the table. Direct from, I didn't understand your question. Can you just explain your question again? Could you have solved without making the table? No, you can't. So in this game, where you have this uncertainty, okay, you have uncertainty because of this decision node, right? You don't know, player 1 doesn't know which node he or she is on. So there is a lot of uncertainty. So how will you rationalize this? If you think about it, player 1 doesn't know. If see, in this game also, if player 1 had a dominant strategy, right? For example, if strategy X were giving him a higher payoff, say suppose here the payoff was 2,5 for Y instead of 8,5. Okay, then you can say that player 1 has a dominant strategy X, which is always giving him a higher payoff irrespective of which node he's on, right? If player 2 plays A or player 2 plays B, and if the strategy X is giving him a higher payoff, then you can simplify it and you can say that, strategy Y will never be played by player 1. So then you may not need to make the table. I mean, whether you make the table or not is actually up to you. And it's also up to the question. If you're asked to make the table in the question, you will make the table. I'm not talking about just this course. I'm talking about in general. Okay. So in this course, anyways, you guys cannot be asked to make the table. So it's fine. So if you're asked to make the table, you can make the table. But if you have to eventually solve only for Nash equilibria, then you for Nash equilibria also, actually you need to make the table, because many times just looking at the game, it's not in a game tree, it's not so easy to identify Nash equilibria just from the tree, because you don't know which one is the which one is the best response of both the players. Not so easy to identify. So you should make the table anyway. But for subgame perfect equilibrium, you ideally would, it's just easier to identify it visually. Okay. You can identify it even otherwise. I mean, I mark the arrow, I make it, it makes it easier for me. I make fewer mistakes that way. But if you want, like, you can also just mark the best responses and see which strategy is actually getting played. What did you ask? Can we reduce it to X for player one irrespective? Yes, that's what I'm saying. So if in this question, that is not the case. But if you have a scenario like here, what I mentioned, like if the payoff for strategy Y after strategy A at this point, if the payoff is 2, 5, then we know that strategy X is actually giving a higher payoff to player one, irrespective of which node he's on. I don't remember what is given in question 2 or 3 in the assignment, and I can't help you with the assignment today, but we can discuss it next week if if you still have a doubt. So, okay, so the game table actually helps you with identifying the best responses. It's just best to use the table here. But for subgame perfect equilibrium, you definitely need to look at the game tree and see which arm of the tree is being played. Okay, so I'll leave this question here, and I'll be back in a few minutes and we'll pick it up from here. Okay, so let's go back to where we were. So, okay, so this is what I've called as a centipede-like game. And this is like a very interesting game because in this game, there are, I think, three stages or three decision nodes. And at every decision node, the player has the option to continue or to just exit. Okay. And that is kind of how we have uh, labeled the strategy. You can say A and D can be accept, decline, or something like that. This is just the notation which is used in this particular question. But the basic philosophy of a centipede-like game, or um, this category of games, is that there are multiple decision nodes, and at each decision node, if there are two players, then they're kind of alternating between the decision nodes, and at every decision node, they can either choose to continue or they can choose to exit. They can exit. Okay. So this ultimatum game, which we studied in the lectures, can become a centipede-like game if it becomes a question of not ultimatum but a bargaining question, right? So some of the bargaining questions can be modeled in this type of a way, in which instead of the payoffs which I've written, the payoffs would be something like, a division of some, like, dividing a pie or something like that. Okay, we'll come to that also. We'll come to the ultimatum game. But how we model this, or how we draw this, represent this kind of a centipede-like game in the normal form, is what I want to address first. So now, in this particular question, what do you think are the strategies of the two players? You can just type it out. You can take a few minutes to think if you want. So you have three decision nodes. Player one starts first, then player two chooses, and then player one chooses again. Yes, I mean, I'm just asking you more like notationally, in notation, in terms of the notation given: A, D, alpha, delta, small a, small d. What do you think are the strategies of both the players? Player one, you're saying A, D, and D. Why only D? So what we've, yes, but when you're characterizing a strategy of a player, you have to characterize their strategy in every subgame. So D, he is out, but what if, somehow he makes a mistake and, he lands up in the next subgame? You have to characterize that also. That is the whole point which I wanted to address. I mean, we've been talking about it all this time, but like, I think Professor Vimal, I think, explained it in the class. I'll just repeat that. It's sort of like, if, say, suppose you have to nominate somebody to play the game for you. Okay. So say, suppose I can't go to playing a game. Say, suppose maybe it's a game of poker or something, and I have to send somebody with written instructions for what they need to do if they were playing instead of me. Okay. What all they need to do? They need a complete map or a complete characterization of what decision they need to take in every circumstance, right? So if I give them just D, and for some reason that person is not able to choose D, then they need to know what to do at the next decision node, right? In the first stage, okay, choose D, but what to do in the next step, A or D, right? So you have to characterize the whole game in or the strategies in the whole game for every player. Okay, so let me first draw this game. Okay. Let me open the game. So, this can also be drawn like this. This is the same thing, but I'm just going to draw it the way it is in the question right now. So I don't think you have any question like this in any of the books. Maybe there is. I don't know. At least I didn't see it in Osborne or Watson. And I personally find Osborne and Watson to be the better books for this particular concept. I'm not marking arrows right now because we're using arrows to indicate which part of the game is getting played. Okay, so you may find arrows everywhere, but I would prefer to use arrows only if that part of the game is actually being played. It's not wrong, it's just question of preference. This is your game tree extensive form. Now we write down the game table. So let me just mark it roughly here also. This is DA. Okay, so this is the same game. I'm just, instead of drawing it like a tree, I've just drawn it like this, like a centipede. Okay, so let's write the game table. So what are the strategies of player two? Before I make the game table, what do you think are the strategies of player two? Alpha and delta, yes. Great. Okay. So these are the four strategies of player one. This is our game table. Let's see, how do we fill this game table? Okay, so I will leave it here for a moment. I will give you 2-3 minutes to fill out this game table. Okay, and then I will, unless you already did that in the break I gave. So have you already written down the game table? Oh, okay. So let's take a few minutes, because if I just keep writing, I mean, it's okay. It's a nice thing to listen to, like a podcast. But this is not exactly a podcast. I want you to get the concepts right while we are in the class. Okay. So I will just give you 2 minutes. I'm leaving the screen on. Just fill this game table, and then I will fill it, and you can compare and see if you got it right. Okay, so let's fill this table. I hope you have more or less finished by now. Okay, this is the game table. So did you get this? Did you get the same table? Okay. So you can, try to solve some of these questions after the class also. That's why I try to bring slightly different type of questions so that you have a little bit more uh, practice. A, D, delta. Okay. Yes. So in A and D, sorry, what did you say? A, D, delta. No, I think I have got it wrong. Oh, no, no, it's correct. Yeah. Yeah, I was just checking if I made a mistake somewhere. Yeah. Okay, so because delta is played, so the rest of the subgame is not played. So we enter the numbers like this. Now let's first look at the subgame. Okay, I'll come to the best response analysis and Nash equilibrium and all that. But let's first look at the actual game. Okay, so let's look at the last part. Let's do the backward induction thing. So in the last subgame, player one has to choose between A and D, right? Now player one is only going to look at his payoff, and D definitely gives him a better payoff. So 3 is the best response here. So he's going to play D over here. Now this part is extremely important in this type of a game. So pay attention, okay? So if one has to choose between A and D, he's always going to choose D because D is giving him a higher payoff, right? Now 2 has to choose between alpha and delta in the previous subgame. Now 2 knows that if 2 chooses alpha, 1 is going to choose D, right? 1 is not going to play the part A. So even though 2 can get a higher payoff if 1 chooses A, 2 cannot choose A. Only 1 can choose A. And 1 is not going to choose A. 1 is going to choose D, right? So 2 has to compare his payoff between alpha and delta, knowing that 1 is going to choose D in that part of the subgame. Now he'll compare his payoff between this and this because this is 2, right? We're talking about player 2. So obviously he can see that this is higher. He's not going to choose alpha. He's going to choose delta because delta is giving him a higher payoff, and he knows that if he chooses alpha, 1 is going to choose D, and he's going to end up with 3 instead of 4. Now we know that this part of the game gets played. Okay. Let's come back to player one in the previous subgame now. Now one has to choose between capital A and capital D. Okay. Now one is only going to look at his payoff. One knows that if one chooses capital A, 2 is going to choose delta. 2 is not going to choose alpha at all. So that part of the subgame is not going to be played at all. Only the delta arm is going to be played, where I have marked that blue arrow. So one has to compare his payoff between 1, 1 and 0, 4, because if one chooses A, 2 chooses delta, he gets payoff 0. Whereas if one chooses D, he gets payoff 1. This is the best response of 1. So what happens is that in the end, the whole game does not even get played. It ends here. And this is your SPE. Because, well, one takes an exit, right? And one takes the exit, one takes D, option D, then one gets 1 and 2 also gets 1. So this is a very interesting game. You may say that what's the point of this game? But this is how a lot of lobbying, how a lot of how a lot of games are played eventually. So you can see that if they had actually ended up playing the whole game, and if one had eventually reached here D, if one had reached the last subgame and chosen D, both the players could have actually done much better. They could have gotten a payoff of 3,3 instead of 1,1, which they are getting right now, right? But that does not happen. Why? Because we know that both the players are rational, and both the players know that both the players are rational. And only because of this concept of rationalizability, we know that this part of the game will not be played. In the beginning itself, one is going to take an exit D. So this is the SPE. Okay, this is the equilibrium which the game is going to achieve. Now, if you are asked to find the Nash equilibria, you can do that. 2 is playing strategy alpha. This is one's best response. 2 is playing delta. This is one's best response. And 1 is playing A. A, this is the best response. Playing B. B, this is the best response. This and this. Right? So you get these two Nash equilibria. dA comma delta, dD comma delta. Okay, these are the two Nash equilibria. So you can report it if you want. You can report it. The only reason why we cannot write subgame perfect equilibrium in the same way is because that part of the game does not get played. These are your two Nash equilibria. But the subgame perfect equilibrium is just this. Okay, you see, this is yeah. So this kind of ends here. Okay, so is this clear? Is this game clear? Okay, so there's one more thing I think I forgot to mention in the previous game. Yeah, in this particular game, we did not look at the subgame perfect equilibrium for these two parts, X and Y. So just to go over it once, if we know that, let me erase this to avoid confusion. If one has to choose at this node, then one is going to choose Y, right? And if one has to choose at this node, one is going to choose X, okay? So this is going to be one's response, best response at these two nodes. So I don't remember how many we found, but I'm not sure if I got it. I wrote it correctly. I think I did. Yeah. So I've written the correct thing as a subgame perfect equilibrium, but it's also important to identify it on the game tree, because this kind of makes it visually, much more striking. So if you're choosing, if 2 is choosing B, then 1 is not going to play Y, is going to play X. Okay. So this part you still need to keep in mind. I remembered in the break that I forgot to mark it in the game tree. So just wanted to point that out. Okay, so let's go to the next question. So I also wanted to check, do you actually, I mean, do you still have doubts about the Bertrand oligopoly, or is that okay? Because if you want to explain me to explain that also, then it will take a bit of time. So I'll do that first. How we write its equation. Um, okay, like what equation? I'm not sure I understood your question. Okay, like that. So you will be given like the inverse demand function. Okay, so let me do the Stackelberg game first, and then whatever time is left, I'll discuss the Bertrand game. Actually, I have not written down the Bertrand game because I couldn't find the proper question anywhere. So I'll just write the general form game and explain it. Yeah, so we'll do Stackelberg first, and then I'll just go over Bertrand once, because Bertrand is there's nothing very special about it in the sense that when the two firms are picking their prices and the quantity is it's given by the inverse demand function basically. So it's there, I think it's there in the Osborne book, if I'm not mistaken. I can't find which page it is on, but it is there. Stackelberg. Because I remember I studied from Osborne long ago, but I remember studying it from Osborne at that time. So yeah, I can't find the page, but I think it is there in Osborne. No, it won't be P1 plus P2 because they're both setting their own prices. Okay. It's not going to be, you can't do it the same way. So they're both choosing their own prices for the quantity Q. So you will write the payoff of each firm. It will be P1 into Q minus C into Q, and P2 into Q minus C into Q. I'll go over it. I have it in some other notes I have, but I can't find like a proper full-fledged question for it. That's why I didn't put it in the slides. Okay, let's do the Stackelberg game first, and then we'll look at Bertrand. So the ultimatum game, I'm leaving this question. If I thought we had time, I would have taken it, but it's actually pretty much the same as what's in the slides. What's in the lectures. It's just in continuous form. It's a real X and C are real numbers. So if you have understood the ultimatum game, I will leave this part out. Okay, so in this game, which I've taken for the Stackelberg game, we are taking convex costs, which means like costs are a quadratic function of quantities. And as usual in Stackelberg, we are assuming player one without any loss of generality. We can assume that player one is leader and player two is the follower. And you are given that this is the inverse demand function, which you are given. Let me write it down. Oops. So although we're talking about this in the context of industrial organization, we're talking about a duopoly or oligopoly. This model of a game has applications beyond just industrial organization. We use the same kind of model in other things also. Okay, so we are given price as a function of quantity as alpha minus Q. Q is kit demand. Okay, and we are given that this is for Q is less than or equal to alpha, and price is equal to 0 if Q becomes greater than alpha. Okay. This is what you're given. You're given the cos Ci as a function of Qi as C Qi square. Okay, so Q where I is equal to 1, 2. This much is given. Okay, so now we know that instead of capital Q, we can write Q is equal to Q1 plus Q2, where 1 is reader, 2 is follower. All right. So we know that. Let's draw this in the game, extensive game form. Here we are taking, of course, Q1, comma Q2 belong to positive real number. It can be any number as long as it's a positive number. Okay. So this is your basic setup of the game. Now I'm drawing it in the form, extensive form, and we show it like this. So Q1 picked by 1 first, and 2 knows what Q1, what 1 has picked. Okay, player 2 is acting here, and player 2 knows the value of Q1. Okay, we are showing this to represent the form, the fact that there are infinite number of strategies available to player 1, because Q1 can take any number of values. We'll come to that upper cap on capital Q right now. If you don't have that upper cap, you can actually make it a bit different here. This part you can say is capital Q, and this is, you can say, 0. So 1 has the choice of Q1. It is choosing something over here, Q1. Let me erase this. Understanding what I'm doing, right? I just put an upper limit on Q1. That's why I erased the dotted line and I made that solid line, and I wrote capital Q. And the range is between 0 and Q. We're just trying to show that diagrammatically. It's chosen some value Q1 between 0 and Q. And here 2 does the same thing. 2 has options also between, so this is like, let me redraw this. Q has the option to choose between 0 and capital Q minus Q1. Okay, whatever that value may be. We don't know what capital Q minus Q1 is. Okay, so this is the basic form of the game. Now let's write the profit function of both the firms. So price we know is alpha minus capital Q, which is Q1 plus Q2. I'm just simplifying this. Okay, and now let's write the profit function of 1 is what? PQ1 minus CQ1. P is this value, alpha minus Q1 plus Q2 into Q1 minus CQ1. And phi 2 is Q2 minus CQ2. Or wait, let me simplify this further. This is CQ1 square. Actually, we've taken cos as convex. I just realized that in our question, we have cos as quadratic function of quantity. So this should be CQ1. C function Q2. Okay, this is what was I saying? Yeah, alpha minus Q1 plus Q2 minus C Q2 square. So is this part clear? This is just the profit function. We haven't done anything yet. Okay, so this is same way as you had proceeded in the, I think in the lecture also. I don't remember exactly, but I think this is sort of what we did in the lecture. Now we will start with backward induction, right? We want to start with player two's choice first, right? So what we'll do is player two can only control Q2. He cannot control Q1. Okay, he only has the power to choose Q2. So he will maximize his profit with respect to Q2. Okay, so here we will differentiate this with respect to Q2. If you want, we can simplify this further, but I'm just leaving it as is for now. Okay, so this is the relation we will get. This is the condition for maximization of profit with respect to quantity Q2. Okay, let's just simplify this. Q2 is equal to alpha minus Q1. Remember, we are doing a slightly different example from what you had in the class, in the lecture series, because what you have in the class you already know. This is a quadratic cost example, so it's slightly different. So you can say that this is best response of 2 given Q1 is this. Remember when we had tragedy of commons, we did something like this. It's a similar kind of a thing. Now we will solve the other way down. We will solve for Q1 also. And we know that Q1 knows that Q2 knows that Q1 will be choosing to maximize their profit. And player one also knows that player two will be maximizing their profit given Q1. Okay, so let's see. Phi 1, where is it? You're just rewriting this value. I'm just writing the way we wrote it. Now we can plug in the value of Q2 here because he knows, one knows that 2 will be doing this calculation to optimize. If you want, you can put a star here to optimize their payoff, right? So pi 1 is equal to alpha minus Q1 plus what is Q2? Alpha minus Q1 upon 2C plus 1. We haven't really differentiated or anything for here yet. We are just writing the profit function first. Have I made a mistake? Yeah, this is going to be here. This is the whole thing is the price in the square brackets. Whole thing in the square brackets is the price as a function of Q1 multiplied by Q1 is the revenue of firm 1 minus CQ1 square. Do you not differentiate first and then substitute? You have a good question. I'm not sure. I think it should work the same way. Okay, it may be easier then, but you may miss out on important terms. I think it should be this way. So frankly, I have not had time to solve this question before the class. I'm just going step by step how it should be done. I don't think that it should be a problem. I mean, conceptually, I'm just thinking if there is some problem with this, because this is the best response of 2 anyway, right? So I don't think there should be a problem. Anyway, if we run into problems, we will see. So honestly, I'm not the type of person who will mug up a question and teach you here in the class. Most of the times I try to solve the questions before the class because I want to make sure that there are no mistakes or something in what I'm teaching. And also to make sure that I actually have an answer, because some questions don't have an answer, they're unsolved. So I try to solve them so I have the answer with me, but otherwise I don't mug up things. So, I just sometimes just solve it in the class, and if we have a problem, we have a problem. It's fine. So this differentiation is not very pleasant, but let's try to do it anyway. But Q is minus. Yeah, this is not very pleasant. Not at all. This is, I think, correct. Minus. Let me rewrite it. Now let's do d by 1 by 2. Okay, so you can just collect the terms. This question is unsolved actually. In the book, it's just given as an exercise for the reader. It's not solved, but I wanted to take something different, so let's remove this part. So I took this question. 2 plus 2, or we can actually cancel this part. This 2 gets cancelled. Yes, you're asking me something. Second term is positive. Why will second term be positive? Which one are you saying? Second last term. Second last term. Second last term here. Oh, here. Yes. This is the one you're saying, right? Yeah, sorry. Thank you. And that was a mistake. Let's rewrite this. I lost thread of where. Good to know you're solving along with me. So let's collect all the Q1 terms first. Minus 2 plus 1 by C plus 1 minus 2C is equal to, let's take alpha on that side, 1 by 2C plus 1. This is what we get. We can switch it, and this, you can, if you want, you can flip the sign. Might be easier that way, and you can simplify it, and you get some solution for the, you simplify the algebra and find the value of Q1. And when you know the value of Q1, you can, if you want, you can plug it into this to find the value of Q2 star. So, I mean, the value is algebraically what it comes out to be. It comes out to be. But I wanted to talk about how we actually go about doing it. So I was thinking about what you said, if you can leave it as Q2. But the thing is, Q2 is a function of Q1. So when you are trying to differentiate pi 1 with respect to Q1, and you just plug in Q2 as Q2, you will make a mistake in the differentiation, right? Here, if you want, I'll just explain it a bit in this expression. In this expression, Q2 Q2 is a function of Q1, right? So if you want to write it as Q2 also, you will still need to write Q2 as a function of Q1. And then when you differentiate this with respect to Q1, you will need to do dQ2 by dQ1 also, which is why you can't plug in just Q2 as is and then substitute its value later. You understood what I'm saying? So this is a common mistake people make in multivariate calculus. So in this kind of a question, we generally have to be a bit careful. Now I'm like, this algebra is a bit messy because we took like convex cos and things like that. So, you know, you can simplify it, whatever value you get, that is your Q2, that's the value that is your Q1. Based on the value of Q1, you can compute the value of Q2. So once again, after the class, because this is like a bit of messy algebra, I will just check my calculations if it is correct. And if it is correct, it's correct. If it's not, I'll correct it. But I think it should be fine. I think it should be correct. So I'm leaving this here. I will, because we have only like 5-10 minutes left. So I'm just going to introduce Bertrand a bit to you. Okay, let me just open the part where the basic structure of Bertrand was given. Okay, so this is the basic function. Okay, there are two firms, and each firm sets its price pi. Okay. And the firm with price pi less than pj gets you know, the whole market share as per gets market share as per demand function, right? The other firm cannot sell. This is the unique part in Bertrand. So imagine if there is some good, okay? I have not written down every assumption, but you can just listen. There are two firms, they're selling exactly the same good. For example, like assume they're selling something like safety pins. There's not much product differentiation, right? One safety pin is almost exactly like the other one. Now they're selling some good like that, and each firm only gets to control their price. Okay, so they're setting prices P1 and P2. And if P1 is less than P2, and say suppose demand function, let me write some demand function. I'm just taking the one which is there in this particular question, 1 comma P2. So demand function can be anything. I'm taking the one for the question which I have in my notes, but it can be some other function also. Just bear that in mind. In this case, you can see the demand function is 1 minus P. It can be A minus P, alpha minus P, whatever the hell you want it to be. Okay. And if both the prices are same, then they divide the quantities, right? Both sell by 2 by 2. And if Pi is greater than Pj, then the quantity of I is 0. Okay. Is this much clear to you? Because if this part is clear to you, the rest of it is not going to be very difficult. Yes, so this is all you need to understand, that the quantity you can sell in the market is decided based on the price you are setting. Now, I was looking for some proper question, but you know, if say suppose the here, because we are taking the function as 1 minus Pi, there's P will have to be like a continuous value. But say suppose we take some discrete value. If it is some discrete value, the question becomes very different. I'm just thinking of what type of a question to take. This is like a very general question. No, Coke and Pepsi is not the question. Coke and Pepsi is almost the same thing. Like, what exactly do you mean, Coke and Pepsi? What is the exact question? I was looking for a question with the discrete values, actually. I don't want to make up numbers because sometimes that goes wrong. So I was looking for something which we can use. Okay, so let's say suppose this is A. Okay, I'm not putting 1, I'm putting some value A. A is greater than 0. Okay, let's say it's that. So you know that your upper limit is basically price cannot be greater than A. That much is clear, right? Now say suppose this question is given to you as quantity is market quantity. Say suppose 10 minus P. All right. Now you have to if Coke is less price than Pepsi, say 9 and rupees 10, you're saying Coke will sell 100%. Yes, that is exactly what I'm saying. So if firm 1 is, we're saying, but theoretically there will be some sales. So we're not talking about that type of an example where theoretically there will be some sales. That is the whole point of Bertrand Duopoly. That is what price competition is all about. So even in Coke and Pepsi, you have to consider the taste and preferences of the buyers, right? In the situation in which you are saying that there will still be some sales, if some people are brand loyal to Coke or to Pepsi, they will buy Coke or Pepsi irrespective of what the price is. But we are not considering those type of things, right? Only those people will buy, right? Are you understanding what I'm saying? That's why I didn't want to take the example of Coke and Pepsi because they're two major brands. Not like that's why I said, say there is an example of something very ordinary, like safety pins or like, say a water bottle like this. If there are 4-5 brands making exactly the same water bottle, and I am not partial to any of those brands. They're all the same to me. Then I will buy the bottle which is the cheapest, right? And so will everybody else. Quality is the same, product is the same, if they're just different companies. So, okay, I will discuss this more in the next class if you want, because we are almost out of time. And I don't want to rush through this because this part requires a little bit of careful consideration. And let me see, I think, I had some question in some notes somewhere, but I can't find it right now. So this is the general form. Now you can, of course, write the profits of both the firms like this. Pi, you can just write pi 1. If P1 is greater than P2, pi 1, costs are 0. We are assuming costs are 0 for now. Okay. Pi 1 is what? 0, because his price is more, right? And pi 2 is whatever the quantity is, A minus P2 into P2. It's correct, right? This is what happens. And if you have if you want to flip it, you can write it the other way around. If P2 is greater than P1, then it will be opposite. And if P1 is equal to P2, then both of them are going to divide it up, right? Pi 1 is equal to A minus P1 by 2 into P1, and pi 2 is equal to A minus P2 by 2 into P2. We're writing quantities here, right? So quantity is divided into half. So in the end, especially if this is in continuous values, then both firms have an incentive to always undercut the other firm. What we mean by undercutting is like reducing the price less than the other firm. So what happens in the equilibrium is a mystery. I'm leaving it as a mystery. I know what happens, but I don't want to give it away. I want you to just solve this question and just think over it a little bit. think about what actually happens in this situation. And then I will discuss it again in the next class. Because like I said, it requires some careful thought. So I don't want to rush through it, and I don't want to just post the solutions. Okay, I'll take 5-10 minutes in the beginning of the next class to discuss this, and I will bring some proper discrete values for a question so we can make the game table and all that. Okay, so I think it's almost time, and we have covered almost everything we had to cover today. So I'll end the class here unless you have any questions. Okay. All right, then. Thank you. Bye.